I thank you all for watching my videos. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We will now discuss the solution of a problem from the question paper CSIR National Eligibility Test held in the month of June 2023. This question is from the section Linear Algebra and it is related to the concepts of determinant and eigenvalues of a matrix. This question is from the part B, which is a multiple choice question, and it carries 3 marks. The question ID is 704029. This question is suitable for all these examinations. Right. The given question is, let capital A be a 3 by 3 matrix with real entries. Which of the following assertions is false? We are given 4 options. Option 1, A must have a real eigenvalue. Option 2, if the determinant of A is 0, then 0 is an eigenvalue of A. Option 3, if the determinant of A is negative and 3 is an eigenvalue of A, then A must have 3 real eigenvalues. Option 4, if the determinant of A is positive and 3 is an eigenvalue of A, then A must have 3 real eigenvalues. Right. We will now discuss the solution of the problem in detail. We are given capital A, Aij 3 by 3, where Aij belongs to R. It is a 3 by 3 real matrices. It is a real matrix. Agreed. Let us take the options one by one. Option 1, A must have a real eigenvalue. Is it so? Yes, it is. How do you say that? A is a real matrix, that is the entries are real numbers of order 3, that is it is a 3 by 3 matrix. Then its characteristic equation of A is an equation of degree 3 which is odd with real coefficients. So the characteristic equation of A is an equation of odd degree, that is 3, with real coefficients. We recall a result. An equation of odd degree with real coefficients has at least one real root. So the characteristic equation of A has a real root. This implies A has a real eigenvalue. That is, A must have a real eigenvalue. Thus, the option 1 is true. Let us take the second option. If the determinant of A is 0, then 0 is an eigenvalue of A. Is it true? Yes, it is a known result. But anyway, we will show you that it is true. Odd determinant of A is 0 implies determinant of A minus lambda is 0 times I3 is equal to 0. Determinant of A is 0. This implies determinant of A minus lambda I3, where lambda is 0, is equal to 0. That means lambda is an eigenvalue, that is 0 is an eigenvalue of A. That is, if A is a singular matrix, then 0 is an eigenvalue of A. Thus, the option 2 is also true. Right. We move on to the next option in the next slide, that is option 3. This time, if the determinant of A is negative, determinant is negative, and 3 is an eigenvalue of A, one of the eigenvalues is 3, then A must have 3 real eigenvalues. Is it so? Yes, we will show you it is true. Let it is a 3 by 3 matrix. Therefore, 3 eigenvalues we consider, lambda 1, lambda 2, lambda 3, be the eigenvalues of A, and it is given one of the eigenvalues is 3. Let us take lambda 3 is equal to 3. And it is very well known that the product of the eigenvalues is equal to the determinant of A. So, determinant of A will be lambda 1, lambda 2, lambda 3. And it is given determinant of A is a negative and one of the eigenvalues is 3, that we said lambda 3 is equal to 3. The determinant is the product of the eigenvalues lambda 1, lambda 2, lambda 3. One of them, that is lambda 3, is 3. That will be 3 times lambda 1, lambda 2. And it is given determinant of A is negative. So 3 times lambda 1, lambda 2 is negative. It will imply lambda 1, lambda 2 the product lambda 1, lambda 2 is negative. Now 3 is already a real eigenvalue. Will the other 2 eigenvalues are real? If you say it is so, then our option 3 is true. We consider the following 3 cases. The first case is, one of these 2 eigenvalues is complex and the other is real. Case 1. One of lambda 1, lambda 2 is real and the other is complex. Case 2. Both the eigenvalues lambda 1, lambda 2 are complex. Then in that case lambda 2 is lambda 1 bar, that we will show you. And case 3, both lambda 1, lambda 2 are real with opposite signs, because lambda 1 multiplied by lambda 2 is negative. Both lambda 1, lambda 2 are real with opposite signs. So these 3 possibilities. So we say the first case is not valid. Case 1 does not arise. Why? Because the complex roots of an equation with real coefficients occur in conjugate pairs. Therefore, one of them is real and the other is complex, does not arise. So, lambda 1, lambda 2, if they are both are complex, then they are in complex conjugate pairs. So, in case 2, both lambda 1, lambda 2 are complex and lambda 2 is equal to lambda 1 bar, because the complex roots occur in conjugate pairs when the coefficients are real. So, let us take lambda 2 is equal to lambda 1 bar. Then lambda 1, lambda 2 is negative, will imply lambda 1 multiplied by lambda 2 is lambda 1 bar is negative, that is mod lambda 1 square is negative. Now for a complex number, the modulus, can it be negative? No. For a complex number, its absolute value, modulus, is always non-negative. Therefore, this is not possible because the modulus of a complex number is non-negative. Thus, we have overruled the first two cases. Therefore, for the third case must be true. That is, both lambda 1, lambda 2 are real with opposite signs. And the lambda 3 is already, we have taken 3, and that is the real. So, thus, we'll get all the 3 are real eigenvalues. Thus, all the 3 eigenvalues of A are real. Thus, we have proved the option 3. It is necessarily true. So, the option 3 is true. Now, so far we have seen the first 3 options. Option 1, option 2, option 3. They are all true, and we are asked to find out a statement, an assertion which is false. Therefore, the option 3, the assertion given in option 3 must be false. The assertion given in option 4, option 1, option 2, option 3, they are all true. By elimination, the option 4 must be the false statement. What is that option 4? If the determinant of A is positive, in option 3 it is negative, in this case it is positive, 3 is an eigenvalue of A, then A must have 3 real eigenvalues. This must be the false assertion. So therefore the answer to this question is option 4, because we have to find out an assertion which is false. So that is the detailed discussion of the solution of this problem, and the problem is over. But our students will ask the question, sir, how do you say the option 4 is false? Yes, that I will show you in the next slide. We will show you now option 4 is false. If the determinant of A is positive, the option 4, and 3 is an eigenvalue of A, then A must have 3 real eigenvalues. As in the earlier case, let us take lambda 1, lambda 2, lambda 3 are the eigenvalues of A, and lambda 3 is 3, and given determinant of A is positive and 3 is an eigenvalue of A, determinant is equal to the product of the eigenvalues lambda 1, lambda 2, lambda 3. Lambda 3 is 3. So 3 times lambda 1, lambda 2 is the determinant of A, which is given to be positive. Therefore, 3 times lambda 1, lambda 2 is greater than 0. This will imply lambda 1, lambda 2 is greater than 0. This can happen, but the eigenvalues lambda 1, lambda 2 must be complex numbers, complex conjugates. This is possible when the matrix has a pair of complex conjugate eigenvalues, non-zero complex conjugate eigenvalues. Then 3, one of them is real, these 2 will be complex, and thereby your option 4 is false. But if you want a counter example, I will show you. For example, you take a matrix A, 3 by 3 matrix, whose first row is 3, 0, 0, second row is 0, 0, 1, the third row is 0, minus 1, 0. So the characteristic equation of this matrix is lambda minus 3 into lambda square plus 1 is equal to 0. So what are the eigenvalues? 3 is an eigenvalue, lambda square plus 1 is equal to 0, that is lambda is equal to plus or minus I. So the So, the eigenvalues of A are 3 plus or minus I. Thus, the assertion given in option 4 is false. Is false. This is same. You see, this is possible when the matrix has a pair of non-zero complex conjugate eigenvalues. For them, this is true. For that, this is an example. And this argument tells us the assertion given in option 4 is false. We are asked to find a false assertion. Therefore, the answer to this question is option 4. And that is the detailed discussion of the solution of this problem from the section linear algebra, which is related to the concepts of determinant and eigenvalues of a given matrix. I am sure that you have understood the solution of this problem. I thank you all for watching this video. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We hope to meet you all in another episode of learning. I wish you all the best. Thank you.